Good morning. Today we're going to get a start on section 5.1. And today we look at one of the fundamental problems of integral calculus, so the second branch of our calculus class. And the one main facet of integral calculus has been what we're talking about, this idea that derivatives and antiderivatives are inverses of each other and kind of cancel each other out. The other main topic in integral calculus, though, deals with the following. Deals with area under a curve. So area under a curve. And believe it or not, this concept of trying to be able to calculate the area under a curve leads us to all kinds of different applications that we can use to answer questions in physics and all kinds of areas of science. All right? Now, I've got a couple pictures drawn on the screen there, and if we were trying to find the area under a curve, which is a straight line, so this first one is just a plain old straight line, and if we choose certain points, like if I asked you to find the area between A and B, not very difficult, and in fact, we'd be able to make that calculation, that area calculation, fairly simple because this shape is just simply a triangle. And we know that a triangle has an area of 1/2 times the base times the height. Or on my second picture, if I asked you to find the area between two values, whatever they might happen to be, right? Again, under a straight line, we'd be able to accomplish that. Now the shape is a little more complicated this time. The shape that models the area this time is actually a trapezoid. But from geometry class, we have a formula that does that for us, so we'd be able to find that exact area. But the problem that's really plagued math for an awfully long time, actually this goes back to Archimedes. He was trying to figure out a method to get this exactly, is how to calculate the area under a curve. So as an example, here's a curve represented by function f. And if I asked you to look between two values, I'll just choose A here for the heck of it, and I'll choose B over here for the heck of it. How do we find the area under a curve, all right? Something that's not a straight line, right? And a method that's been used for centuries was to try a method of approximating the area by putting in shapes that we know. As an example, if I put in a rectangle across from where f of A is, we, of course, know how to find the area of that big rectangle, and that takes care of a lot of our problem. But then we could start putting in other shapes. As an example, maybe I could find this point right here and find the area of a triangle like that, or we could draw another line up and have, so we could find all these individual areas and add them up. But no matter what you do, you're always going to have these little sections that you can't quite or have a difficult time accounting for. So you'd have all these little wedges and shapes and pieces that would be you'd have a tough time adding up. All right, and so we need a method for calculating areas under curves without just trying to force shapes that we know into that space and try and continue to do it. And in fact, the method that's demonstrated here, the one Archimedes used and a lot of other mathematicians have used, is actually called the method of exhaustion, believe it or not. All right, and I think I spelled that right. If I didn't, sorry. But exhaustion, the idea is you'd continue to put in smaller and smaller known shapes until you've used up or calculated the entire area, which is really next to impossible. So we need a method for doing this. All right, and here's the idea. Here's what we do in calculus. Right, I'm going to start by giving you a specific function. So I'm going to give you y is equal to 1/4 x squared plus 1. And this entire lesson is going to be asking you to help me find or approximate the area underneath that curve on the interval from 0 to 4. Okay, and so I'm just going to get a relatively decent sketch. So 1/4 x squared plus 1 is a parabola that starts up 1 from the origin, and the 1/4 means that it's a parabola that's flattened out a bit, and it doesn't have to be perfect or anything, but it just gives us the idea. And then what we're looking for is the area from 0 to 4. Okay, and so we're looking to calculate the area underneath the parabola in between 0 and 4 above the x-axis. That's our job. That's what we're trying to do. Okay? Now, what we can do to approximate that to start with is to break the interval from 0 to 4 into equal sub-intervals. And what I'm going to start with here is I'm going to start by breaking it into 2 sub-intervals. All right? And our sub-intervals are always going to be equal, so that means I'm going to make a break, cut this equally into 2 chunks, so I'm going to draw a line at 2. So we have this 0 to 2, and then 2 to 4. Those are equal. Okay? Now, to approximate the area, we have all kinds of different ways we can do this, but what I'm going to use is what's called a lower sum. And what's going to happen is, in each of the intervals, we're going to pick a point on the curve. Let me select my arrow. We're going to pick a point on the curve, either this point on the left side of that interval, or this point on the right side of the interval. And when we're using a lower sum, when we use a lower sum, we're going to pick the lower of those 2 points. So which of these 2 points, this one or this one, is lower? Well, it's the first one. So what we do is we create a rectangle across from that value. When we move over to the next interval, which one is the lower point? This one on the left side of it at 2, or this one on the right side at x equals 4. Well, which one of these is lower? Obviously this one. So what we do is we create a rectangle by drawing a horizontal line across from that point. So what we've just done is we've created 2 rectangles, and to approximate the area, what we're going to do is find the area of those 2 rectangles and add them together. Please notice that each rectangle is 2 wide. All right, each rectangle is 2 wide, so length times width. The width for each rectangle is 2. But what's the length going to be? Well, the length is going to be the vertical height of the rectangle. So for the first one, I just marked it in blue. That would be the length of the first rectangle, and the second one would be that one. And how do we find those lengths? Well, those are points on the parabola, so what we do is we input the x value for each of those into the original function. So I'll put 0 into the original function. So 1/4 times 0 squared plus 1 is 1. So the length of that first rectangle is 1. What's the length of the second rectangle? Well, that belongs to x equals 2. So we put 2 into the original function. So 1/4 times 2 squared plus 1. 1/4 times 2 squared is 1, and 1 plus 1 is 2. So when we do the calculations, the area of the first rectangle is 2, the area of the second rectangle is 4, and when we add those together, we get an area of 6. Question, is that approximation, 6, too big or too small compared to the actual area? Well, it's going to be too small because we're not taking into account this little wedge section, and we're not taking into account this wedged section. So we're short of the actual area by those 2 little blue wedges. So we have an understanding that the lower sum is too small. Well, next what we're going to do is we're going to find the upper sum. All right? Once again, we're going to use the 2 sub-intervals, so we're going to have 2 rectangles. So we'll have length times width, length times width. All right, the widths are still going to be 2 because we're using the same sub-intervals, but now the lengths, when we choose an upper sum, have to be the higher of the 2 points every time. So if I switch to red, now when you look at the first interval between 0 and 2, now we pick the higher of the 2 points. So the higher of the 2 points this time is this one that I'll mark in red. And when I create a rectangle by bringing the line across, right, we have that rectangle. And when I move to the second sub-interval, which point is higher? It's going to be this one. And so I'm going to create a rectangle from that point. All right? Once again, the widths of each of those 2 rectangles is 2. But what is the height? Well, the height of the length of the first rectangle now belongs to x equals 2. So let me put that in red. So that belongs to x equals 2. And when we put 2 into the function, 1/4 times 2 squared plus 1 is 2. And for the second rectangle, the higher of the 2 points belongs to x equals 4. And what's the length of the rectangle when x equals 4? Well, 1/4 times 4 squared plus 1 is 5. So when we calculate the areas, 2 times 2 is 4, 5 times 2 is 10, and 4 plus 10 is 14. Would that approximation be too big or too small? Well, it's way too big because we're overdoing it by this much, and we're overdoing it by this much. We've overdone the areas. So the blue wedges force us to have an underestimate for the lower sum. The red wedges force us to have an overestimate for the reds. So the actual area has to lie in between 6 and 14. Agreed? The blue made it too small. The lower made it too small with the blue wedges. The upper, with the red wedges, made it too big. So the actual area has to be somewhere in between. Okay? So can we get any better? Can we do any better? Sure. One thing we could do is we can increase the number of subintervals. So what I'm going to do now is take the exact same curve, not changing anything, same curve, 1/4 x squared plus 1, so same picture. I'm just going to choose to draw the right-hand side of it since we're looking from 0 to 4. Just going to choose to draw the right side of it. So 0, 1, 2, 3, 4. So we're still looking for that area, but now instead of 2 subintervals, let's go with 4. So if I go with 4 subintervals, now we're going to break that into 4 equal intervals. So of course that means I pick nice easy numbers. That means we're going to draw a vertical line at 1, 2, 3, and then we still have the 1 at 0 and 4. Okay, and once again we're going to calculate a lower sum. Right, but this time since we have 4 subintervals, we're going to have 4 rectangles. So 1, 2, 3, and 4. What's the width of every one of the rectangles going to be this time? Well, the width is going to be 1 every time. It's the complete interval divided into 4 equal chunks. So the width of every one of the rectangles is 1, right? And how do we determine the length of every one of those? Well, what we're going to do is we're going to pick because we're doing a lower sum, we're going to pick the lower of the 2 points that makes up every interval. So the lower of the 2 points for the first interval is going to be this one. So we're going to create the rectangle by drawing a line across. The lower of the 2 points for the next interval is going to be this one, so we draw a rectangle across. The lower of the 2 points for the next interval is going to be this one, so we draw a rectangle across. And the lower of the 2 for the next interval is going to be this one, so we draw a rectangle across. Okay? And therefore the length of every one of those rectangles is going to be the point that belongs to the lower of the 2, right? And the way I've set this up with an increasing function, that's going to be the point to the left every time. So for the first rectangle, we get the length by using x equals 0, 1/4 times 0 squared plus 1. For the second rectangle, we use the point to the left, which is 1, so 1/4 times 1 squared plus 1 is 5/4. For the third rectangle, we use the point to the left, which is x equals 2. And when we put in 2, 1/4 times 2 squared plus 1 is 2. And for the last rectangle, we use the point to the left, the shorter one, which belongs to x equals 3. So 1/4 times 3 squared plus 1 is 13/4. Right? And what we're going to do is multiply all of the lengths times widths. So 1 times 1, 1 times 5/4, 2 times 1, and 13/4 times 1. And when we add all of those folks together, we get, I believe it's 15 halves, or if you prefer the decimal in this case, 7.5. But is that estimate too big or too small compared to the actual area? Well, it's too small because we're not taking into account all of these little blue wedges. We haven't taken into the account, so we're under the actual area. We're underneath. Okay? So next we're going to go to an upper sum. And again, using the 4 subintervals, that means we're going to have 4 rectangles. So we're going to add up 4 length times widths. The widths, once again, are 1. They're all equal. And then the lengths we're going to find using the higher of the 2 points. So for the first rectangle, we choose the higher of the 2 points to create the rectangle. For the second rectangle, we use the higher of the 2 points. For the third rectangle, we use the higher of the 2 points. For the fourth rectangle, we use the higher of the 2 points. And again, because of the way I've set this up, the higher of the 2 points belongs to the point on the right of each of those subintervals. And so we're going to put in those numbers, 1, 2, 3, and 4, into the original function to get the lengths. So now the length of the first rectangle that I've outlined in red is going to be 1/4 times 1 squared plus 1. So it's going to be 5/4. For the second rectangle, we use the number to the right, so that's a 2. So 1/4 times 1 squared plus 1 is going to be a 2. For the third rectangle, we use 3. So 1/4 times 3 squared plus 1 is 13/4. And finally, for the last rectangle, we use 4. So 1/4 times 4 squared plus 1 is 5. And once again, we're going to do the multiplication. 5/4, 2, 13/4, 5. And when we add those together, I believe, if I'm doing the math okay in my head, we get 23 halves, I believe, or 11.5. Is 11.5 too big or too small compared to the actual area? It is too big because we're overdoing every one of the rectangles by the red wedges. We've overdone it, right? We've included too much area. Therefore, the actual area of our triangle has to lie somewhere between 7.5 and 11.5. All right? And if we scroll back, remember our range of values when we had 2 subintervals was 6 to 14. Our second range when we used 4 subintervals was 7.5 to 11.5. We essentially cut the interval where our actual area is in half. We cut it in half. And of course, what we're going to do in calculus is we're going to continue to increase the number of sub-intervals. All right? Now, I'm not going to force you to sit through the entire calculation for the next one, but I'm just going to give you the results for taking the same curve, same interval. So everything's staying the same, everything has stayed the same, but instead of 4 subintervals, we could go to 8 subintervals. And so we'd have to divide our interval into 8 equal parts. So if we put in the lines that we had last time, that's 4. And then we'd have to chop each of those in half again, which would then make 8. Okay? And once again, we could calculate a lower sum, and we could calculate an upper sum. Unfortunately, this time, because we've divided it into 8 equal intervals, what we'd have is 8 individual areas added together. For both the lower and the upper, we'd have 8 individual areas added up. Again, I'm not going to force you to sit through this whole thing, but I'm just going to summarize. What would the width of every one of the rectangles be now? Every width is going to be a half. Every one of the widths would be a half all the way across. So every width is a half. Okay, and of course, what's going to change is the lengths. For a lower, we're always going to use the lower of the 2 points. And I'm just going to try and get you the feel for that as I go across. So those would be the lower of the points. And we'd have to then go through all of the different values and put them in. As an example, for the first one, we'd put in 0. So 1/4 times 0 squared plus 1 is 1. For the second one, we'd have to use 1/2. So 1/4 times 1/2 squared would be 1/16 plus 1 is 17/16. And we just continue that all the way across. Now, again, I'm not going to force you to sit through this whole thing, but when we find the lower sum and punch it out, we get 8.375. Okay? The upper sum, we'd have to choose the higher of the 2 points every single time and create the rectangle. So we'd use the higher of the 2 points, all right? And so the very first one this time is going to be the 17/16. And I'll get you the next one. The next would be using x equals 1, so 1/4 times 1 squared plus 1 is 5/4. And again, you just do that for all 8 rectangles. And when we add all of those son of a guns up, what we get is 10.375. The blue, too small because we're not taking into account all of those little blue wedges. That's too small. Reds, too big because we're overdoing it by each of those little red wedges. So once again, the actual area is going to fall somewhere in between 8.375 and 10.375. Right? And if you look back, you can see that the interval on which the actual area lies continues to go down, down, down. We started with a distance of 8, I think it was from 6 to 14, and then a distance of 4 between 7.5 and 11.5, and now we have a distance of 2. All right, if anybody's curious, I'm only going to move the screen a little bit. The actual area underneath this curve on the interval from 0 to 4 is exactly 28/3. Is exactly 28/3, or approximately 9. I guess it's not approximately, actually, it's exactly equal to 9 1/3. What I meant to do was approximately equal to 9.3. Right? So the exact area is that value. All right? And we will learn how to find that area throughout this chapter. We're going to learn how to find that exact value. Okay? Now, there's all kinds of different ways in which this area can be approximated. I chose to show you what are called lower and upper sums, but there's all kinds of other ways to do it as well. All right? We could have used what are called left and right points. So we could have done the same thing with left points, but you might notice that because of the curve I chose, if we chose the left points, that would be exactly the same as the lower sum. And of course, we could choose right points as well. So for a curve like this parabola, it looks the same, and you're thinking, what the heck, it's exactly the same. But if we have a curve that goes both up and down, so if we have a curve, even if we take something simple like the sine curve, and we look from 0 to pi, that's a curve that goes both up and down. So as an example, if I broke this into 4 equal subintervals, we could use lower sums, pick the lower of the 2 points in every interval. We could use upper sums, the higher of the 2 points, but we could also do things like pick left points. So we always pick the point on the left to create the rectangles, right? And you end up with this kind of weird combination of some of the rectangles are below and some of the rectangles are above. So the thought might be, well, geez, maybe that kind of averages them out and we get a better answer right off the bat. So all kinds of different ways that we can get this done, and we'll talk about more of those tomorrow. I didn't want to make you sit through too much of this just basic computation stuff, so I'm going to call it a day there. If you want to, go ahead and try a couple. The first few problems in your assignment are actually ones where you have to use the graph from the book. So give them a try, see what you think. Otherwise, I'll be back tomorrow, and we'll take care of more of these together. All right, so I hope you have a good day, and we'll talk to you tomorrow.